Alright, so let's look at a few more examples utilizing the binomial distribution approximation using the normal probability distribution. So for this first example, suppose that more than a decade ago, high levels of lead in the blood put 78% of children at risk. A concerted effort was made to remove lead from the environment. Suppose, according to the survey, only 6% of children in the United States are at risk of high blood levels. In a random sample of 150 children taken more than a decade ago, what is the probability that 105 or more had high blood lead levels? So the first thing we need to do is make sure this is a binomial probability, and then that we can use the normal approximation. So to do that, let's check and see, do we have a fixed number of trials? In this case, we had 150 children, so we have our fixed number of trials is 150. And this random variable, those trials are going to be independent, so we meet that criteria. Next, we want to define success, and that's going to come from the probability that we're interested in. So here we're interested in the probability that 105 or more had high blood lead levels. So we're going to define success to be that. So we're going to say success is high blood lead levels, which now lets us define what our probability of success is going to be. So our probability of success is the likelihood that you had high levels of lead in the blood, which is 78%, or 0.78. And then Q is always 1 minus P. So here that's going to be 1 minus 0.78, which is 0.22. So we have a binomial probability, and we know what NP and Q are. The next thing we need to check are what are our values of N times P and N times Q, and make sure that they are both greater than or equal to 10, so we can use the normal approximation. So if we do N times P here, that's going to be 150 times 0.78, which is 117. And that's certainly greater than or equal to 10, so that one's good. The next one, N times Q, so that's 150 times 0.22, which is 33. That's also greater than or equal to 10, so we're good. So the normal approximation applies. So the next thing we want to do is find the mean and standard deviation of our binomial random variable, which is going to be the same mean and standard deviation we're going to use for our normal random variable. So our mean, remember you get this for free, so mu is N times P. So we've already found that, that's 117. And our standard deviation is the square root of mu times Q. So that's going to be the square root of 117 times 0.22. And so when we evaluate that, we get the square root of 25.74. So if you were to calculate your variance first, that variance would be 25.74, which is then 5.07. So those are the mean and standard deviation we're going to use. Now we want to find the probability that we're looking for in binomial and write that out in probability notation. So we're looking for the probability that 105 or more had high blood lead levels. So this is the probability that R is greater than or equal to, since it's 105 or more. So R is greater than or equal to 105. Here we already have equality, so we're good. So we've checked the equality piece. So now we can go on and do that continuity correction to convert to our normal distribution. So this is going to be the probability that x is greater than or equal to some number. And so we want to ask ourselves, is 105 a left-hand or a right-hand endpoint of the interval? So you can always draw it out on a number line if you're struggling with that. So 105, and we want it to be greater than or equal to 105. So that's going to be everything above it, which means 105 is on the left. So because 105 is a left-hand endpoint, we're going to subtract 0.5 from that 105 when we convert to normal. So this is going to be 104.5. So the probability that R is greater than or equal to 105 is the same thing, or it's going to be close because we're approximating the probability that x is greater than or equal to 104.5. Now we're back to the same steps that we've done before because we're back in a normal probability distribution. So these are going to be the same steps that we had for 6.1 through 6.3. So now we go from x to z, so going from that normal distribution to our standard normal distribution of z. So z is greater than or equal to, now we're using that z-score formula. So our data value of 104.5 minus our mean of 117 divided by our standard deviation of 5.07. So that gives us the probability that z is greater than or equal to negative 2.47. At this point, you want to sketch and see what you're looking for. Make sure that it matches the picture that you have in your tables. So since we're graphing a z probability, we know our mean is the z distribution is 0. We're at negative 2.47, so we're somewhere down below the mean and below our inflection point. And because we're looking for the probability that z is greater than or equal to negative 2.47, we know that's going to be area to the right. So we shade in our right-hand side. Now remembering our table only ever gives us area to the left. That means this is going to be 1 minus the number you get off of your table whenever you look up negative 2.47. So when you go to your normal distribution table, you look up negative 2.47, you should get 0.0068. So the probability we're interested in is going to be 1 minus that 0.0068. And so when we do that, we're going to get 0.9932. Alright, so let's look at another example. Suppose that 62% of the people who were murdered actually knew the person who committed the murder. Suppose that a detective file in Boston has 62 current unsolved murders. So we want to know, what is the probability that fewer than 33 victims did not know their murderer? So for this problem, again, we want to set up our binomial probability. So looking for n, our fixed number of trials. So we had 62 trials because we have 62 unsolved murders. Next, we need to define what success is. So remember, that's always going to come from the probability you're looking for. So we're looking for the probability fewer than 33 victims did not know their murderer. So we're going to define success as they did not know their murderer. And then we need to find what P and Q are. So P, probability of success, that's the probability somebody did not know their murderer. So let's look at the information we're given. So we're told that 62% of the people who were murdered actually knew the person who committed their murder. So we actually, in this case, are given our Q value. We're told that you do know the murderer. So that means Q is going to be 0.62. So then P, because P and Q are always complements, our probability you did not know your murderer is going to be 1 minus Q. So 1 minus 0.62, which is 0.38. So now we want to make sure that n times P and n times Q are both greater than or equal to 10. So in other words, that the normal approximation applies. So n times P is going to be 62 times 0.38. And that gives us 23.56, which is greater than or equal to 10, so that one's good. In Q is going to be 62 times 0.62, so that gives us 38.44, which is also greater than or equal to 10. So because both of these are greater than or equal to 10, the normal approximation applies. So now we want to find the mean and standard deviation of our binomial random variable. So our mu, remember, that's n times P. So we already calculated that when we were checking, so that's 23.56. And then our standard deviation is going to be the square root of mu times Q. So that's the square root of 23.56 times 0.62, which is 3.82. So now let's go back and find the probability we're looking for. So we're looking for the probability that fewer than 33 victims did not know their murderer. So that's going to translate to the probability that R is less than 33. Now we want to stop and look at it. So we don't have equality here. We only have strictly less than. So we need to rewrite this binomial probability to have equality before we do that continuity correction. So being less than 33, that's the same thing as saying you're less than or equal to 32. So now we can do our continuity correction. So this is going to be approximately the probability that a normal random variable is less than or equal to, and then we want to find out, is 32 a left-hand or a right-hand endpoint? So again, you could draw the number line, see which side 32 sits on that interval, or you can look at the direction that your inequality is opening. Since this one opens to the right, we know 32 is a right-hand endpoint. So that means then we add 0.5 to it. So this is going to be the probability that x is less than or equal to 32.5. And then do our conversion to z. So this is the probability z is less than or equal to our data value, 32.5, minus our mean of 23.56, divided by our standard deviation of 3.82. And so if we do that calculation, we get the probability z is less than or equal to 2.34. So now we sketch that out, make sure it matches the picture on our table. So there's our z, there's our 0, and our z-score is 2.34. And then we want probability z is less than or equal to, so that points to the left, so we shade to the left. And so since this is area to the left, we can just take our table value. So if we do that, if we look up 2.34 on our table, we get 0.9904. Alright, so let's look at one last example. So assume that about 45% of all U.S. adults try to pad their insurance claims. Suppose that you are the director of an insurance adjustment office. Your office has just received 102 insurance claims to be processed in the next few days. What is the probability that more than 49 of the claims are not padded? So same idea. We want to set up our binomial probability. So our binomial piece first. So we need to know what n is. So n is our number of trials. So we have 102 claims. So 102 trials. Next, we want to define success. So look at the probability that you're given. So we want to know 49 of the claims are not padded. So we're going to define success to be not padded. And then use that to define our P and Q values. So in this case, this is just like the exact last example. We're looking for the probability that our claims are not padded, but we're told 45% of all U.S. adults try to pad their claims. So again, we are given our value of Q, which is 0.45. So then P is going to be 1 minus Q because they're always complements of each other. So that's 1 minus 0.45, which is 0.55. Now we can check our NP value and our NQ value to make sure they're both greater than or equal to 10. So N times P is 102 times 0.55, which is 56.1. So that's definitely greater than or equal to 10. And N times Q is 102 times 0.45, which is 45.9. That's also greater than or equal to 10. So our normal approximation applies. So next, find our mean and standard deviation. So our mean, N times P, we get that for free, so that's going to be 56.1. And then our standard deviation, square root of mu q, or square root of N times P times Q. So that's going to be the square root of 56.1 times our Q value of 0.45. And so we get a standard deviation of 5.02. Now let's write out the probability we're looking for. So we're looking for the probability that more than 49 of the claims are not padded. So that's the probability R is greater than 49. So again, we have to make equality here. We don't have equals yet. So saying you're bigger than 49, that means you're greater than or equal to 50. Next, we convert to normal, so we do that continuity correction. So that's the probability that x is greater than or equal to 49.5. So because if we think about it on the number line or looking at which way our inequality is opening, 50 is going to, since we're looking at greater than or equal to 50, 50 is going to be a left-hand endpoint, so we subtract that 0.5 to do that continuity correction. And then now we're back to normal, so we just convert from normal to standard normal, going from x to z, using our z-score formula. So probability z is greater than or equal to our data value, which is 49.5, minus our mean, which is 56.1, divided by our standard deviation, which is 5.02. And so that's the probability that z is greater than or equal to negative 1.31. And now we sketch that distribution out. So z, 0 is always in the middle, negative 1.31. We're below our left-hand point of inflection, but just slightly. And then we know it's z greater than or equal to, so that means area to the right. So because it's area to the right, it's going to be 1 minus the area in the table for negative 1.31, which in this case is 0.0951. So 1 minus 0.0951 gives us 0.9049.